Okay, the last section we're going to take a look at this week is 11.2. We'll do part today, part tomorrow. And 11.2 is on what we call a series. So series is just when you take all the numbers in a sequence and you add them up. The goal is going to be to figure out a quick way to do that. If your sequence only had 3 or 4 numbers in it, well, that's easy. You can just add them up manually. It doesn't take that long. What if your sequence had hundreds of thousands of numbers in it? Okay? We don't want to plug each number in one at a time and add them all up. Okay? So we're gonna try to find a formula that can add up all the numbers for us. Okay? We're going to talk about 2 kinds of series. A finite series. Finite means it has an end. Okay? So if a sequence has an end, then it definitely adds up to something. Even if there's millions and millions of numbers, you can add them all up because they stop somewhere. Infinite is a little different. When you add up infinitely many numbers, at first that kind of seems like, well, if you add up infinitely many numbers, then it would just add up to infinity because you're adding up an infinite amount of numbers. Sometimes that's true, but not always. There are times where you can actually add up infinitely many numbers and then you get an answer like 7. Okay, so you can do that. So today is going to be finite, and then tomorrow will be infinite. Okay, so in the last section, we used a lowercase letter when we were naming a sequence. And then a formula might look something like this. N represents the position in the sequence you're trying to find. So if you wanted to find the first term in this particular sequence, you would plug in 1 and then do it up. So let's do the first just 4 or 5 terms. If we plug in 1, what's 2 times 1? 2 minus 1. And then if you square it, 1. So that's the first term. If we plug in 2, 2 times 2 is 4, minus 1 is 3. And then what's 3 squared? 9. You know what, I'm just going to write it as 3 squared. It is 9, but let's leave it as 3 squared for now. If you plug in, let's see, that was 1, 2, third term. 2 times 3 is 6. 6 minus 1 is 5 squared. So the pattern here is odd numbers squared. Okay? And if you did them out, you would have 1, 9, 25, 49, 81. Right? And it keeps going. Right? So that's how you use a formula to write the terms in a sequence. So any questions how we got those numbers? Okay. So now we're going to look at adding these numbers up. And we can control how many we want to add up. Do you want to just add up the first one? Do you want to add up the first 2, the first 3, the first 4? Okay. We can specify how many we want to add up. And this is the notation that we use to specify add up the first n numbers. Okay? S stands for sum, and n is the number of terms you want to add up. So if we wanted to find S sub 1, okay, for what's circled in purple right there. S sub 1 means to take what's in purple and add up the first 1 terms. Well, the first term is just 1 squared. It just adds up to 1. So when you're adding up the first 1 terms, there's nothing to really add up. It's just the first term. S sub 2 means to take this one and that one and add them together. So 1 squared plus 3 squared, which would give me how much? 10. Yep. S sub 3 means to add up the first 3 terms. 1 squared, 3 squared, 5 squared. So we're going to be adding 25 to what we just had. So what would that add up to? 35. Okay, and let's just do one more. Let's do S sub 4, just so we have one more. S sub 4 would mean to take the first 4 terms of what's circled in purple and add them up. 1 squared, 3 squared, 5 squared, 7 squared. Yeah, so we already got this part right here. That's 35. That's 49. So if we add those together, we get 84. Okay. And then if you wanted to go all the way to the nth term, well, we don't know how many there would be, so we would just add the first one, the second one, the third one, the fourth one, the fifth one, and we would just keep going until we finally get to the last one they want us to add up. So this represents adding up n terms, where n is a number, right? We just don't know how high. Maybe n is 600, 700, 800 terms. We don't know, but that's why we put dot 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 to represent an unknown amount of things we're going to be adding up. All right. So now what we would do is we look at 1, 10, 35, 84. 1, 10, 35, and 84, that is a new sequence of numbers. That sequence of numbers represents adding the first n numbers up. So the question now is, can we find a pattern in these numbers? That's what we want to be able to do, right? So that way, if we wanted to find like s sub 200, I don't want to have to add up 200 numbers to figure out what that is. I want to look at the ones I already added up and see if I can find a pattern. 1, 10, 35, 84. See if there's some kind of pattern to it. Right. That's going to be the goal. Any question on that? Okay, so that one would be a little bit of a tough pattern to figure out. We'll maybe, I don't know if we're going to talk about what the pattern would be for that. That one's a little tough. So each one of those things that we just found, that is called a finite series. Finite means that it has an end to it. Okay? S1, you're adding up the first 1 terms. S2, you're adding up the first 2. S3, you're adding up the first 3. Finite means there's a certain amount of things you're adding together. It's not going on forever. It's stopping. Now, this thing that I just underlined in purple, the sequence of partial sums, that is what I wrote down right here. 1, 10, 35, 84. At least in our particular problem. It's a sequence of numbers that was figured out by adding up the first 1 numbers in that sequence. The second number, 10, was calculated by adding up the first 2 numbers in that sequence. S sub 3 we got by adding up the first 3 numbers, and S sub 4 by adding up the first 4. Okay. So the name of this sequence is called a sequence of partial sums. Any questions on how we got the 1, 10, 35, 84? Okay, we're going to do another one in a minute, but it is going to be one that we could figure out the pattern for a little bit easier. Okay, when you're adding up numbers in a sequence, you can add up the first 1 terms, 2 terms, 3 terms, 4 terms, 5 terms, 36 terms. You can add up as many as you want. But again, the goal is to figure out a way to do it quickly and not have to do it by hand. This last one right here, this represents adding up the first n terms. Well, how many is n? We don't know. Maybe it's 200, maybe it's 1,000, maybe it's 200 million terms. But it stops somewhere. So writing this down is okay, but the problem is it starts to get really long. Like if you wanted to represent adding up the first 300 terms, we don't want to have to write out 300 things added together. Okay? It'd be nice if we had a quicker way to write that down, and we do. Okay? We're going to look at something that's called sigma notation. Okay? Sigma notation is a quick way for writing down, adding up a bunch of numbers. Okay? The downside of this is it doesn't actually give you a fast way to add up the numbers. It just gives you a fast way to write down that you want to add up the numbers. That's all that it does. Okay, and the reason it's called sigma notation is because it uses a capital Greek letter, sigma, which looks just like that. And there are 3 parts to it. There's something on the bottom, there's something on the top, and there's something on the right side. What's on the bottom is basically telling you where to start. We'll do an example in a minute, and it'll make sense. So the bottom number is basically telling you where to start. The top is going to be a number, and it's telling you where to stop. On the right-hand side, you're going to have a formula, okay? And they're gonna tell you what that is. Okay, so sigma notation is just a compact way of expressing the idea that you want to add up a lot of things. Yeah, important to understand it doesn't actually give you a fast way to add them up. It just gives you a fast way to say you want to add them up. That's all it is. Okay, and the way that you pronounce that is you start by pronouncing the Greek letter in the middle, the sigma, which stands for sum. And it's a sum from k equals 1 to n. So you're starting at this number, you're going to stop at that number, and then they're going to give you a formula. Okay, and we'll do an example right now. Okay. This isn't a very long one, because we're only going to be adding up 5 things. Okay. But in general, we could add up 5 million things. Right? So what you want to do is you start with this number at the bottom. That number at the bottom is called the index. It tells you a value that you're going to plug in to your formula on the right-hand side. And you're going to start with that value. So in our problem, we're starting with 1. Okay. Let's fill in 1 for k. If we fill in 1, what's 2 times 1? 2 plus 3. 5. That's the first number you write down. And then every time you plug in a number, you always put a plus sign after it. Now, you're going to take the number that you started with, and you're going to make it go up 1. You're going to keep making this number go up 1 and plugging it in until you get to the number at the top. So if we started at 1, the next number we go to is 2. So let's plug in 2. What's 2 times 2? 4. And then plus 3? 7. Okay, now we bump it up another one. So we were at 2, now we go to 3. 2 times 3? Plus 3? 9. Okay, we're watching that top number, because once we hit that, that's where we stop. Okay, we were at 3, we're going to bump it up to 4. What's 2 times 4? And then 8 plus 3? 11. And now we're going to go up to 5, and that's the last one. That's where we stop. What's 2 times 5? And 10 plus 3? 13. So this means exactly the same thing as that. This is called sigma notation on the left. This is called expanded notation on the right. Expanded is when you do it all out. Any question on how we got 5, 7, 9, 11, 13? Now, if I wanted to represent adding up the first 5,000 numbers in this pattern, I could write down what I want to do by going like this. That's it. That represents adding up the first 5,000 numbers in the pattern. Now, if I actually wanted to get the answer, well, we still don't have a good way to do that yet. But we at least have a short way of writing down this without writing 5,000 plus signs and adding up every number. Okay, well, I mean, it's a lot more compact up here. Okay, any question on that? All right, actually, that's what I just told you a second ago. When you write something in with that capital Greek letter, that's called sigma notation. And then if you actually do it out like we did, that's called expanded notation. Okay, I wouldn't ask you to expand something that's that huge. I mean, I'm not asking you to expand something that had 10 numbers in it, but I wouldn't ask you to expand something that had like 50. That's just going to take a while. Okay, so any question on the difference between sigma notation and expanded notation? Okay. All right, so let's try this one. This time, we're starting at 1. We're stopping at n. Okay, we don't know what n is. So n is a value, it's some value, they're not telling us what it is, but it does stop somewhere. So what I generally do is I do the first 3, and then I put a dot, dot, dot. And then I'll just plug in this. This represents the last value you're going to plug in for k. Okay. All right, what's the first value we're going to plug in for k? 1. What's 2 times 1 plus 3? 5 squared. Yep. I'll just leave it as 5 squared for now, and then we can simplify it if we want to. Let's plug in 2. What's 2 times 2 plus 3? 7 squared. And let's do one more. Let's plug in 3. What's 2 times 3 plus 3? 9 squared. Okay, so you've established the pattern. 5 squared, 7 squared, 9 squared. I can tell that it's odd numbers squared. Now, there could be a bunch more terms. I don't know how many more. But now we're going to plug in the last thing for k. What's the last thing that we plug in for k? N. Whatever n is. We don't know what it is. It's a number, but they're not telling us what it is. So now plug n in. And that's 2n plus 3 squared. And then once you tell me what n is, I could figure it out. But that's how you expand a sum that has a letter at the top. Do the first 3. I mean, you could do the first 4, first 5, but 3 is good. First 3, dot, 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 and then just plug in the last one. Okay. Any questions on that? Okay. All right, so we're going to look at a few different properties that we can use with sigma, okay, with summations. Okay, and the first one looks kind of like distributive property. It's not really distributive property. But it basically is giving you a formula for 2 different ways that you can add up numbers in a sequence. I'm going to do an example with 2 very short sequences to show you how that works. Let's suppose a sub k was the sequence 135. Okay, just very short sequence. And b sub k was the sequence 246. I want to add these sequences together. And I'm going to do it the way that's on the left first. If I do it the way that's on the left, okay, I have parentheses. that means I'm going to do what's inside the parentheses first. I'm going to add all the numbers in sequence A to the numbers in sequence B. What do you think the first term would be if I add these two sequences together?
3.
Yep, you just add them like this. 1 plus 2, 3. And then the next number would be 7. And then the last number, 11. That's the sequence A sub k plus B sub k. It's 3, 7, 11. Okay, that's this part. Now, this sigma means to add up everything that you just created. So we're going to add up 3, 7, and 11. Okay, so let's write that down. So we're going to start at the first term. In our particular case, we're stopping at the third term because there's only 3. So that means to add up 3, 7, 11. What does 3 plus 7 plus 11 add up to? 21. So that's adding up all the numbers in the sequence by first adding up the pairs, getting 3, 7, 11, and then adding the 3, the 7, and the 11 together to get 21. Okay, now I'm going to do it the way that's on the right. Okay, for the way that's on the right, we're doing it in a little bit different order. First, it says add up everything in sequence A. Sequence A is 1, 3, 5. What does 1 plus 3 plus 5 give me? 9. And then it says to add up everything in sequence B. Again, it's only from 1 to 3 because there's only 3 terms in it. That's why it's 1 to 3. So sequence B are the numbers 2, 4, 6. What does 2 plus 4 plus 6 add up to? 12. Now it says to take what you got here and then take what you got here and add them together. So that's 9 plus 12, which is 21. So the point I'm trying to show you is you can add numbers together in a sequence either way. You can add the pairs together first and then add all those up. Or you can add every number in the sequence together, add every number in the sequence together, and then add those two results up. It will always come out the same. Any question on the difference in the way that I did it? It is different ways of doing it, but it's the same result. Okay, and if you can do that with addition, you can do exactly the same thing with subtraction. I'm not going to go through a whole example again with that one, but if you want to subtract two sequences from each other, you can subtract them term by term, or you can do it the way that's on the right. You'll get the same result either way. Okay, so rule 2 is very similar to rule 1. It's basically the same thing.
If you're doing it the way on the right, you're still adding the numbers together and then subtracting the two different sequences?
Yeah, so if you're doing it the way that it's on the right, this part is still 9.
Yeah.
This part is still 12, but then it would be 9 minus 12, which would give you negative 3.
I got you.
If you do it the way that's on the left, you would have 1 minus 2, 3 minus 4, and 5 minus 6. What's negative 1 plus negative 1 plus negative 1? Negative 3. So it still comes out the same. Okay, so rule 1 is for adding two sequences together. Rule 2 is for subtracting. And rule 3 is for multiplying a sequence by a constant. Okay, this I'll do out. So let's take sequence A, 1, 3, 5, and let's let's let C be 4. Let's do this part first. This says to take sequence A and multiply everything in that sequence by C, which I'm just going to use 4 as an example. So A sub k is 135. C times A sub k means to multiply every number by 4. So what's 1 times 4? 3 times 4? 5 times 4? 20. That's the sequence A sub k times 4. Now, this symbol means add up everything that you just did. And there's only 3 terms, so I'm going to start at 1, go to 3. 4 plus 12 plus 20. What's 4 plus 12 plus 20? 36. Okay, so you can multiply every number in the sequence by 4 and then add them up. Or, let's do it the way that's on the right. You do that part first. Add up all the numbers in sequence A. Actually, so I'll come back to the C. I'm going to do that after. Okay, sequence A, 135. Okay, what do we get if we add 1, 3, and 5 together? 9. Okay, so now this part is 9, and you're going to multiply it by C. C times what we just got. So in our case, C is 4. When we added up all the numbers in A sub k, we got 9. What's 4 times 9? 36. You got 36 here. So you can do it either way. So if you want to multiply all the numbers in a sequence by something and then add them up, you can either add up all the numbers in the sequence first and then multiply by your number after, or multiply every number individually and add those up. It'll come out the same way. Okay, so any questions on those 3 rules? So let's try this one. They want us to take these and combine them into a single sum. So what you have in this problem is, this is like rule 1. They're giving you this. They're giving you something that's on the right-hand side. They want you to turn that into the left-hand side. So when you're done, you're going to have a single sum. Notice when you have multiple sums, they each start at the same number. They each stop at the same number. And when you combine them back together, the number you put at the bottom is the same that you had before, and the number you put at the top is the same one you had before. So when we combine these into a single sum, what's going to go in the bottom? K equals 1. What's going to go in the top? N. That has to match what the original problem had. And now this part just says to add the 2 sequences together. Okay. Think of this as A sub k, and then think of this one as B sub k. You're just going to add those 2 together. So when you add them, it's combining like terms. 5k squared. If I add that with the one next to it, are there any like terms? Yeah. K squared. And what's 5k squared plus 1k squared? 6k squared. So we're just putting it back together. The next one, we've got a minus 4. Is there anything I can combine in the other one with the minus 4? Yep, I've got a plus 7. What's negative 4 plus 7? So that's 3. I'm just going to put that there. And then the minus 2k. Is there anything I can combine that with?
No.
No, didn't have anything. That's how you put that all back together as a single sum. Just combining like terms. So any question how we combine those two sums into one using rule 1? All right, so again, this is great that we've got a short way of writing what we want to do, because if we were to write this out, and maybe if n was 1,000, you'd have to write down 1,000 numbers all added together. So this does save you a lot of writing, but it doesn't save you any calculation. If you wanted to go up to 1,000, right now you'd have to plug in every number starting at 1 for k, plug in 1, get the answer, plug in 2, get the answer, plug in 3, 4, 5, all the way up to 1,000, and then get all those answers added up. Okay, it's still gonna take a long time. So what we want to do is see if there's a faster way to add all these numbers up. Okay, so we're going to look at a few patterns. We're not going to be looking at any real complex patterns. We're really just going to look at 2. Let's look at this one. This says to add up every number from 1 to 10. That's basically what that says to do. So what's the first number you'd be plugging in for k? 1. And when you plug it in, well, there's nothing you really do to it. You're just plugging it in, and that's it. That's the number. So you have 1. And then the next number you'd plug in? 2. And you'd do all of them. All the way up to 10. That's what that's having you do. Now, if you're kind of clever, you could figure out a way to add all those up. I mean, it's only 1 to 10, so it wouldn't take that long. But that's going to add up to, yeah, it's going to add up to 55. Yeah. How did you figure that out?
Well, if you take 1 and 10, that makes 11, and then 2 and 9 make 11, and then 3 and 8 make 11. If you do that 5 times 11 times 5 is 15.
55.
Yeah,
Yeah.
whatever.
So you're adding all these up, so you can add them up in any order you want. If you pair them up, 1 and 10, that's an 11. And then if you pair up a 2 and a 9, that's another 11. And if you add up a 3 and an 8, that's an 11. And then a 4 and a 7, that's an 11. And then a 5 and a 6. So you have 5 pairs of numbers that all add up to 11. So that gives you 55. That's a great trick for that one, but that kind of trick isn't going to work all the time. So we need something that can work all the time. Let's write down some of these partial sums. And then I'm going to show you something that does work all the time. What do you get if you add up the first 1 terms in that sequence?
1.
Just 1. How about the first 2?
3.
The first 3?
6.
And the first 4? 10. Let's look at what happens if I plug in a number, if I plug in this number into that formula. Let's start with 3. What's 3 plus 1?
4.
4. What's 4 times 3?
12.
And what's 12 divided by 2?
6.
I just got 6. Let's plug 4 in, and let's see if we get 10. What's 4 plus 1? What's 5 times 4? And what's 20 divided by 2? 10. So now, if you wanted to add up, let's say the first 20 terms here, at least based on what I've shown you so far, this formula seems to do it. It would be 21 times 20 divided by 2. 20 divided by 2 is how much? 10. And what's 10 times 21?
2010. Or, sorry, 210.
210. So as long as that formula works, which it does work, we can add up as many of these numbers as we want, and I didn't have to add anything by hand. I was able to add up the first 20 terms by just filling in the number 20 into a formula.
Is that formula always going to work? Or?
It's always going to work if you're adding up numbers 1 plus 2 plus 3 plus 4 plus 5. If you were adding up different numbers, like, let's say, odd numbers, 1 plus 3 plus 5 plus 7 plus 9, no, that doesn't work. We'd have to figure out a different one.
How would my trick not work? You
What's
said
that?
my trick doesn't work all the time. How would this one? How would it not work all the time? With this? With
So-
down to whatever.
If we start to make this pattern more complex, the idea of pairing numbers at the end doesn't work. So let's say you did something like 1 squared.
You pair the 1 with whatever is at the end, so it'd be 21, and then you divide 20 by 2, which is 10, and 21 times 10 is 11, 210.
Well, that would work for those numbers, but let's look at a sequence of numbers that is a little more complex. Okay? Instead of just adding 1 plus 2 plus 3 plus 4 plus 5 plus 6, let's add 1 squared plus 2 squared plus 3 squared plus 4 squared and so on. So if we do these out, let's see if adding the ends together works. What's 1 in 36?
37.
So that's a 37. What's 4 in 25?
29.
So now we didn't get the same number. Does that make sense? Yeah, so because we're dealing with numbers that are a little more complicated, pairing them up like that, so now you get 4 and 25 is 29, and then if you do 9 and 16, that's a 25. So the trick didn't work this time. So we'd have to figure out something different. But yeah, as long as you're adding up numbers that aren't squared, like 1 plus 2 plus 3 plus 4 plus 5, that trick would always work. But there's lots of other kinds of numbers besides those numbers. So we're going to look at 2 formulas that basically allow you to take something that's in sigma notation and get rid of the sigma and get an actual number as an answer. Okay, because, I mean, sigma notation's okay to write down. I mean, it is a short way of writing down what you want to do. But if somebody's actually looking for an answer to a problem, they don't want to see the sigma in the final answer. They want a number. So it's like, all right, do the sigma out, add everything up, and then tell me what you're really going to get. Right. So let's look at something like this. Let's see what this means to do. So remember, you're going to start at 1, you're going to stop at 6, and you're going to plug in each number going up by 1 into this formula. What do you get in this formula that I just circled if you change the k to a 1?
There's no K.
There's no k. So what do you get?
Incorrect statement.
No, you just get 4.
You just get 4. Yeah. Now I want you to plug in 2 for k in this formula. What do you get?
4.
You get 4 again. And when you plug in 3 for k?
4.
4. And when you plug 4 in for k?
It's just 4.
It's 4. When you plug 5 in?
Not different.
And then when you plug 6 in, it still stays as 4. So this is a formula where it doesn't matter what you plug in for k because this is a constant. It never changes. What's a shorter way of writing 4 plus 4 plus 4 plus 4 plus 4 plus 4?
4 times 6.
4 times 6. 4 times 6. So if you want to get rid of a sigma and your formula has a constant right here, to evaluate that, all you have to do is multiply whatever number's here times whatever number's here. So C times N, and that will be your answer. So that's a quick way, without having to write it out like this, of getting rid of the sigma when it's just a constant added up over and over. Now, the one that we did, this one, when I showed you guys the formula, you weren't adding up a constant, you were adding up 1 plus 2 plus 3 plus 4 plus 5. So in this problem, you're adding up numbers to the first power. 1 to the first, plus 2 to the first, plus 3 to the first, and so on. And the pattern, or the formula that you can use to add up the first n integers is n times n plus 1 over 2. So they gave you a problem like that. And they said add up the first 5,000 integers. 1 plus 2 plus 3 plus 4, all the way up to 5,000. You don't have to do it by hand. Just take the number 5,000 and fill it in right there for n. 5,000 times 5,001 divided by 2. And that will tell you what the first 5,000 integers add up to. And those are the only two formulas that we're going to look at. The one that I gave you, where was it? Right here. 1 squared plus 2 squared plus 3 squared. You're adding up numbers to the second power. There is a formula for that. I did write it down. But we're not going to look at that. Okay? And there's also a formula for adding up numbers to the third power. 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. You can come up with a formula for adding up anything you want. Okay? But the only two that we're going to focus on are those first two. Okay. Any question on the first two formulas? So the formulas, again, they're giving you a way to take something that has sigma and get rid of it. Actually figure it out and get the answer. So let's see if we can simplify this one. So the goal here is to take what we have there and look at these two formulas and find one that matches what we have. Do either one of these formulas directly match what we have on the example 3? No. That's because there's multiple things right here. Two different things being added together.
But it's still K to the first.
Yeah, but it's still K to the first, so it is probably going to have something to do with this one eventually. Right? And there is a constant right here. But what we need to do with that sigma is break it into 2. Just like rule 1. Okay, you've got something that's combined together, 1 sigma. Let's split it into 2. And as we split it into 2, it's going to get simpler. And then hopefully it'll match one of these two right here. Okay. When we split that into 2 sigmas, what's going to be the number that goes at the bottom? K equals 1. What's going to be the number at the top? N. Because we have a plus sign right there. We're going to put a plus sign right there. And what do you think would go in that box for the formula? Negative 2k. And what would go in that box? 3. Okay. Now, does either one of those sigmas now match one of these rules? Which one?
Last one.
The last one, yeah. This last one right here is just saying to add up the number 3 this many times. Okay, when you plug 1 in right here, you get 3. You plug in 2, you get 3. And you just keep getting 3 n times. So if I use rule 1, what does this turn into? 3n. And that's the goal. We don't want the sigma. We want it gone. Okay, so that one's gone. Now, the first one.
Can't you split that again?
How did we split that?
Can you split it again?
Well, we can't split it again, but does this look almost like anything that's over here?
Yeah, the second one.
It almost looks like the second one, but the problem is there's a number right here. We have a -2 in front of the k. This formula doesn't have a -2, it just has a k. So let's go back and look at our rules again. And there's a rule that says if you have a number, like -2, a constant, and it's being multiplied, you can take that number and move it where? You can put it in the front. Yeah. So let's take the number that's inside -2 and let's move it to the front. That's rule 3. Okay, so that -2 is going to go right there. And once we move it, then it should look like something you recognize. So -2. K equals 1 doesn't change, n doesn't change. But what's left inside this box now?
Okay.
Just k. And this is something we have a rule for.
And 10 plus 1 divided by 2.
Right. Whenever you have starting at 1, stopping at n, and you have a k there, you can get rid of all that stuff and replace it with just that. N times n plus 1 over 2. So -2 times n plus 1 over 2. So now you got rid of the sigma in the first part. Don't forget the plus 3n. Okay, and we'll just distribute that and clean it up a little bit. What's -2n times n?
-2n squared.
-2n squared. And what's -2n times 1?
-2n.
Excuse me. -2n. And what is that all being divided by? 2. So I'm just going to go like this. 2, 2. So I divided each part separately by 2. What's going to happen to the 2's in the first term?
Cancel.
Cancel. And the 2's in the second term?
Cancel.
They cancel. So you're left with -n squared minus n plus 3n. But what's -n plus 3n? 2n. And that's your answer. Okay, so what does that formula do for you? Well, let's say that I wanted you to do this from 1 to 500. That means I want you to plug in 1 for k, write down what you get. Plug in 2, write down what you get. Plug in 3, 4, 5, go all the way to 500, and write down every answer that you get, and then add all those answers up. Well, instead of plugging in every number from 1 to 500, one at a time for k, and then adding them all up, all you have to do is plug in 500 for n right there. So do 500 squared, make it negative, and then add 2 times 500, add 1,000. And it'll automatically add up all the numbers for you without doing them one at a time. That's what that formula is. Okay. Any question on that? Okay, so we're not doing the quadratic. You're not going to have any with the second power. So let's just change that to, we're just about done. Let's get rid of the second power. So let's just make it 5k minus 2. Okay, so the goal is to figure out a formula that could automatically add up as many numbers as you want in this pattern. If you can't figure out a formula, and I asked you to go from 1 to 100, then you'd have to plug in every number from 1 to 100 for k, write them all down, and then add them all up. It's not practical. So we're going to get rid of the sigma, and in the end, we're going to have a formula we can just fill a number into, and it'll add everything for us. We're going to break that up into 2 sigmas. What's going to be the bottom number on each sigma? K equals 1. and the top number, or top value, n. And what are we doing with the two sigmas this time? Like what symbol is going to go between them? We're subtracting them this time, because that's a minus. Okay. What's going to go in that box? 2. So that part's done. K equals 1 to n of a constant. That's rule 1. We can already simplify that part. Now, this part. How can I rewrite that sigma so it matches something that's over here? So put the 5 in front, and what would go in this box? Okay. So now, once you get two sigmas that match these rules, substitute in a formula for that and for that. Okay. So we've got 5, and what do we substitute in for this first one?
N times n minus 1, or n plus 1, sorry.
Yep, and why don't we just do it out? So that's n squared plus n divided by 2. Okay, I just saved myself one step, so I'd already distributed out the n. That's all. Okay, and what about that second sigma?
2n.
That turns into 2n. Yep. Okay, I still have got one more thing I have to distribute, the 5. So 5n squared plus 5n, and each one of them is divided by what? 2. 2. This time the 2 doesn't cancel, but I have like terms I can put together. So 5n squared over 2. So 5n, what's 5 divided by 2? 2.5. What's 2.5? N. Take away 2n. Half n. There you go. So now if you wanted to add up the first 100 terms in that sequence, just plug in the number 100 for n, and it'll add them all up for you. All right, any question on that one? All right, so last formula. So these two formulas allow you to add up the same number over and over, and to add up integers, like 1 plus 2 plus 3 plus 4. But what if I had something like this? And I said to add those up. Are you adding up the same number over and over here?
No.
No. Are you adding up numbers like 1 plus 2 plus 3 plus 4 plus 5? No, you're skipping a lot. What's the pattern?
Multiplied by 2.
Right, we're multiplying by 2 each time. And when you have a sequence where the pattern is multiplying each time, what do you call that? What is it?
Like the rate?
So yeah, the R value is 2, but there's a name for the type of sequence. We talked about 2 names yesterday. Yes, that is a geometric sequence. Well, if you wanted to add up every number in this sequence, starting with the first one, all the way to the 5,000th one, you can do that very easily. It's not one of the rules that we had right here. It's that rule. So that's the formula for adding up all the numbers in a geometric sequence. Okay, it relies on knowing 2 things. A1 is the first term in the sequence. And R is what you multiply by each time. So let's try that formula on the one that I just had. How many terms did I just write down on the board? 6. Okay. So let's add them up by hand, and then let's try adding them up with that formula, because 6 doesn't take that long to add up. So we've got 2, 4, 8, 16, 32, 64. And if that's all I had to do, well, I would just do it that way. Adding up 6 terms doesn't take that long. But if you want me to add up 6,000, well, then I'm going to do it the way that's on the right. But let's see if we get 126 using that formula. We're going to add up the first 6 terms. What's the first term there? 2. times 1 minus, and r is what you multiply by each time. What are we multiplying by each time? 2. And n is how many terms you're adding up. How many are we adding? We're adding up 6. 1 minus 2. All right, let's do that out and see if we get 126. So in the top, you've got 1 minus 2 to the 6th. That's negative 63. What's 1 minus 2? Negative 1. What's negative 63 divided by negative 1? 63. And what's 2 times 63? 26. So did it actually save us a lot of time using that formula? No, not in this case, because you're only adding up 6. But if you wanted to add up 6,000, you could do it just as fast with that formula. The only thing that would change is instead of a 6, you'd have a 6,000. Okay. So let's try this one, and let's see if we can add up the first 12 terms. Okay, so 3 things we need. A1, R, and N. What's A1 in this case? 2. What's the R value? Or what are we multiplying by each time? You're multiplying by 1/3. Yep. 2 times 1/3 is 2/3. 2/3 times 1/3 is 2/9. Yep. So multiplying by 1/3. And how many terms are we adding up? 12. Now it's just a matter of filling everything in and figuring it out. So you need your first term. You need 1 minus r to the n. So that's 1 minus 1/3 to the 12th divided by 1 minus 1/3 in the bottom. Okay, the reason why that formula works, that's not something we're going to get into. We just have to apply the formula to figure out the answer. Great, so let's do that out. So we've got 1/3 to the 12th power. So we've got 1/3, let me put it in parentheses. Okay, that gives us that. I don't know if I can make that a fraction. No. So what I'm going to do then, because I can't make this into a fraction, I'm just going to leave that the way it is in the calculator. 1/3 to the 12th power is a very small number. It's 1/3 times 1/3 times 1/3 times 1/3 times 1/3 12 times. So it's very small. And that's what that represents. Okay. Yep.
Couldn't you do like 3 to the power of 12 and then put that in the denominator? Would that work?
Yeah, there are other ways you could do it. Yeah. Yep. What I'll do is, just so I don't have to think about anything fancy, I'm just going to type it all in like that. 3 minus 1/3. Or was that 1 minus 1/3 to the 12th? That's the numerator. And then we're going to divide that by 1 minus 1/3. That's the denominator. And then what's the last thing I have to do? Times it by 2. So if you add up the first 12 terms in this sequence, it's getting extremely close to what number? It's getting very close to 3. So that kind of gives you a hint that what would happen if you didn't add up the first 12? Let's say you added up the first 2,000 terms. Because what you're adding each time is only 1/3 as big as the term before. What you add each time gets smaller and smaller and smaller and smaller and smaller. Eventually it's getting so small, what you're adding doesn't even make a difference anymore. So if you could add up an infinite amount of numbers in that pattern, they would add up to 3. This one adds up very close to 3, okay, but that's the answer. It's not 3, but it gets very close to 3.
How would you write that? Just 2.99?
Yeah, you'd have to write that whole thing. 2.999 994355. Okay, and the more terms you add up, the closer and closer it's going to get to 3. Eventually it's going to run out of decimals, and it's probably just going to say it is 3. But it actually never quite reaches 3. But it gets close. And that's what we'll look at tomorrow, adding up infinitely many terms. All right. Okay, so that's homework for tonight. It's on 601, 1 through 19.
Oh, it's easy.
Okay, so tomorrow we'll do 11.2, part 2. That'll finish chapter 11, and then I'll put a list of topics on the board. And we have our test on